Hello and welcome to another wonderful episode of the New York City Category Theory Seminar. Today we have Emilio Minichiello. This is the third time I think you're speaking.
Yeah.
And we take it away.
Okay, so thanks for having me again, Noah.
Well, anything.
So today I'm going to talk about presenting profunctors. This is a paper. This is joint work with Joshua Meyers and Gabriel, Goren, and Roig. So I'm going to talk about the paper, same name, presenting profunctors. It's been accepted for ACT 2024. Now before I can get into the details of this paper, I want to motivate the discussion. So I need to talk a little bit about categorical database theory, which was the original motivation for this work. So I'm going to discuss this idea. You can say it's due to David Spivak, but the idea had been floating around for a very long time before him, with work by Bob Rosebrook on sketches. But Spivak took this very simple model of database theory. So the idea here is that database schemas are just categories, and database instances are co-presheaves on categories. So let me explain how this works. So let D be this category. So this category has two objects, employees and departments. And it has the following morphisms. It has the following, the morphism manager, which goes from employees to employees. It has the morphism departments, from employees to departments. And the morphism secretary, from departments to employees. And then I want these to hold. So here I'm writing composition in a different way. So this means manager and then manager again. I want that to be equal to manager. And then secretary and then department is the identity, okay? Because the secretary, the department of the secretary should be the department that they're the secretary of, okay? So this is a category, and there's infinitely many morphisms here. Okay, but I'm just showing some of them.
What does the first thing mean? That everybody's their own manager, or everybody's
the manager of the manager
is himself?
It's transitive. No, it's just transitive. So if my boss's boss is also my boss.
No.
Manager. If you are a manager, then you are your own manager.
Oh, God.
My boss's boss
is my boss.
Okay. So it's not my boss, is whatever.
Anyway, so now I have this, and this I want to think of as my database schema. Okay, now my actual database instance is going to be a functor from this category to the category of sets. And so I'm going to give you the data in the following way. So I, on employees, is a set. What's the set? It's the set of employees of this database instance. And there's 3 employees, Alice, Bob, and Charlie. And there's 2 departments, computer science and math. Now, I has to take the morphisms to functions of sets. So I of manager has to be a function from the set I of employees to itself. Okay? So this function is going to send Alice to Alice, so she's her own manager. Bob gets sent to, that should say Charlie up there, that's a typo. Bob's manager is Charlie, and then Charlie's manager is himself. Alice's department is computer science, Bob's department is math, Charlie's department is math. And the secretary of computer science is Alice, the secretary of math is Charlie. All right with everybody? Okay, so this is a functor from D to set. And we want to think about that as a database on this schema. And we can visualize this as a table. So here, this would be like your primary key, okay? And that's the set of employees. So for every object, we're going to get a new table. And we think of the outgoing arrows as the columns here. So my primary key consists of the employees, Alice, Bob, and Charlie. The manager of Alice is Alice, Bob's Charlie, Charlie's Charlie, departments, and so on. Okay? So this is how you can think of categories and co-presheaves as databases.
is not important at all, but I think there's a typo when you define manager on the second line where you say.
Yes, yeah. Yeah, that should be Bob's manager is Charlie. So now, to query data in this categorical data model, we're going to use profunctors, okay? So a profunctor, P from C to D, is a functor C op times D is set. Some people have different conventions, but this is the convention I'm going to use. And notice that this is exactly the same thing as a functor from C op to functors from D to set. Okay.
You didn't say what C is. C is just another schema?
Yeah, so these are both just categories. I'm just telling you what a profunctor is.
No. Okay.
But in this model, categories are schemas, and schemas are categories. Okay? So, how do I talk about this query? Select all employees who are their own manager. I need to come up with a profunctor that emulates this query, right? So what I'm going to do is I'm going to define C to be a category with one object that I'm going to call managers and no non-identity morphisms, all right? Now I'm going to construct a profunctor from C to D, and D is the category I showed before with employees and departments. And I want this to enact that query. Okay? So let's define it. So let P lower star denote the co-presheaf P on managers. Okay? So that's going to be a functor from D to set. So what I'm going to do is on employees, I'm going to set it to be E. I'm going to think of this as like a freely generated thing, and I'll explain more about what that means later when we get to presentations. But right now, it's just a set containing two elements, E and E.dep.set. And then for department, I'm just going to do E.dep. And then the functions are going to be kind of obvious, except when I defined this query, I wanted it to be all the employees who were their own manager. So when I set the manager of E, I'm just going to set it to be E itself. You see that there? And then that's going to also mean that this one gets sent to itself. Now the department of E is just E.dep. And then by this law, you see that the department there is just E.dep also. And the secretary is just the secretary of the department. So imagine this is like a free kind of construction, okay? And we can also represent this as a table. So here we have two employees E and the secretary of the department that E is in. And then the corresponding manager's department secretary. So now, if I have a profunctor from C to D, I obtain a functor that takes co-presheaves on D and gives a co-presheaf on C. So it's going the opposite way. And I define it object-wise as follows. If I have I, which is a co-presheaf on D, and I have an object C, then I set eval of I, so this should be a functor on C to set. So this needs to give me a set, and the set is going to be the set of natural transformations from this co-presheaf to this one. Is that all right? Okay, so, and then the action on the morphisms is easy to read out from this. And this defines a co-presheaf on C, sorry. And we call this the evaluation of I by P, profunctor. So now let's look at our example from before, and we want to compute this eval of I. So we have eval of P of I is now a functor on the category with one object managers and no morphisms. So I have to provide a set, okay? And that set is going to be the set of natural transformations from P on managers, which I also write as P lower star, into I. Okay, so I want to know what is the set of all natural transformations, right?
From a one-object category.
So C was a one-object category. D now has objects and morphisms, right? So being a natural transformation here is non-trivial.
Yeah, okay, fine, sorry.
So both of these, P lower star and I, are both functors on D. And D has employees, departments, and those morphisms.
Those are two, right.
Okay? So let's see, what are some natural transformations? Well, a natural transformation requires that I have functions for every object in D, right? So for employee, I want a function here from P of emp to I of emp. So let's say this function takes E and sends it to Alice. All right, and it sends e.dep.sec also to Alice. Now this actually extends to a natural transformation because this diagram commutes. This diagram commutes because if I take E here and I send it down by this morphism, I defined it, the manager of E, to be E. And then when I send that over, that goes to Alice. And when I send E over to Alice and I do its manager, Alice is her own manager. So this diagram commutes, and you can check that this forms a natural transformation. So that means that this natural transformation will be an element of the evaluation. Now this function that takes P of emp, I of emp, that sends E to Bob, and the department of the secretary to Charlie does not extend to a natural transformation. Why? Because E is supposed to be its own manager, but Bob is not his own manager. Charlie is his manager. This diagram doesn't commute. This is not a natural transformation. Okay?
And you only want to choose those that are their own manager.
Yeah.
Wait, did you already have an instance that you're referring to here?
I, yeah, I.
Oh, you gave that already?
Yeah.
Okay.
I had Alice, Bob, and Charlie, computer science, math.
Right, okay.
So now I have eval P of I is a functor from D to set, right? So then if I evaluate it on employees, I get a set. And that's the set of natural transformations. I'm just going to label them by sending E to Alice and E to Charlie. So these are the two employees who are their own manager. And I can write it as this table. So this is the result of the query that I wrote. Okay? Any questions on that? So from the profunctor, I can think of profunctors as queries that take coprecies to coprecies, that take database instances to database instances. So we're going to add that to the list. Now the example I gave admittedly was pretty simple, but you can imagine these things being quite complicated where before C was only a category with one object and no morphisms, but you can imagine there being morphisms, and these act like foreign keys in a database. So it can actually be relatively complicated.
Can I ask you about?
Yeah.
To me, the first two things pretty much fit into Levier's functorial semantics. I mean, they're souped up. What about the third thing? I mean, Levier doesn't have profunctors. I mean, what would it be in terms of functorial semantics?
I'm not 100% sure. I mean, it's a good question. Yeah, there's been some work on this. Christian Williams knows some stuff about this in general, but it's not something that's I've seen a lot mentioned. All right, so any other questions? Yeah.
The profunctors come long before Spivak. I mean,
Yeah, of course.
Okay.
Yeah. So now, here's a further important property of profunctors. They compose. So the way I like to think about profunctors is as a categorification of relations. So a relation from a set A to a set B is just a subset of A times B, right? But I can equivalently think of that as a function from A times B into the set 0, 1, right? and we can compose relations. Okay, so if I have a relation from A to B and a relation from B to C, I can obtain a new relation A to C by saying A is related to C if there exists a B such that A is related to B by R and B is related to C by S. Okay, so we can compose relations and we can compose profunctors.
Interesting.
So, given profunctors P and Q, we can obtain a composite profunctor using the following Cohen formula. And if you don't know what Cohens are, don't worry about it. But it's very similar kind of idea as the composition of relations.
Well, some sort of a version of the idea of a convolution product.
Okay.
Well, which would be an instance of that.
Right, so now if I have a functor from E to set, and I take the evaluation on the composite, that's actually isomorphic to first evaluating by Q and then evaluating by P.
Yeah.
Sorry? E is just a third category, so P goes from C to D, Q goes from another typo, D to E. So this means we can compose database queries. However, if we want to use the categorical model on a computer, we have to use presentations of all of this stuff. So, you know, a computer can't accept just category theory. So you have to come up with some way of putting it into the computer, right? Mm-hmm. So the main point of this paper is that presentations of profunctors are surprisingly subtle. So let's discuss presentations. All right, so let's get started. That was all the motivation. Now here's the details. So a category signature sigma consists of sets, a set of sorts, and a set of function symbols. And you have two functions called the source and the target, and we write f like this to mean that the source is C and the target is C prime. A path in sigma consists of a possibly empty sequence of function symbols, and we write the composite of them like this. So this is a path P. Okay, and remember, the composition is the opposite than what you would normally think of. So it's F0, then F1, dot, 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 then Fn. Okay? And I'm going to let 1C denote the empty path on a sort C. And I write P from C to C prime if the source of the first function symbol is C and the target of the last function symbol is C prime. And let path of sigma denote the set of paths. And if you know algebraic theories, this is what that is, okay? But if you don't worry about it. This is like a very watered down version of algebraic theories where we only have unary function symbols, and that's where the terminology is coming from. Okay, so a map of category signatures consists of two functions, a function from the sorts of sigma to the sorts of sigma prime, and a function f1 from the function symbols to the paths of sigma prime. Such that if f is a function symbol, then f1 of f is a path with this source and target. And most of the time we're just going to write f instead of f0 and f1. And we're going to extend f to a function on paths in kind of the obvious way. So we take a composite of function symbols like that and the empty one like that. So given a category signature sigma, an equation in sigma consists of a pair of paths P and Q with the same source and the same target. And sometimes we'll even label an equality with their source and target like this, okay? So that was a category signature and an equation. Now a category presentation consists of a pair, C, where C sigma is a category signature, and CE is a set of equations over that signature. So I write P equals lower CQ to mean that this pair of paths belongs to the equations of C.
So you're writing your category as a you know, a quotient of a free category, because what you had with the, we were going before your function sort sounds like basically, in a way, you're talking about free category. Or
Exactly.
data for
You're
a
getting
free
ahead of me,
category.
but yes, exactly.
Okay. Well, I just wanted to connect it with terminology I'll be more familiar with.
Sure. All right, so now we're going to define a relation on the paths of C, okay? Using these inference rules. So if P equals Q is an equation in C, then I'm going to call this relation provable equality. So P is provably equal to Q. P is always provably equal to itself. You have transitivity, symmetry, and then these two other ones where if I have a function symbol and I have two paths, I can compose, and those will be provably equal, and similarly on the left-hand side. Okay? And as I said, this is a provable equality relation. Now, a map of category presentations is first of all going to be a map of their signatures. So it's going to send function symbols of C to paths in D. And I want it to have the following property, that if P equals Q in C, then I can prove that f of P is equal to f of Q in D. Okay? So let cat per denote the category of category presentations. Now, as you were saying, Ray, if I have a category presentation, I can get an actual category out of it. As you said, I can take the free category and then quotient by this relation. That's exactly what I'm doing here. And we call this the category presented by C. Sometimes I'll just call it the semantics of the category presentation. And this construction also defines a functor from category presentations to categories. Okay? So, if I have two maps of category presentations, I write f approx f prime if for every function symbol they're provably equal. So now I'm actually quotienting maps of category presentations, okay? And we say f and f prime are provably equal as maps of category
And by provably
presentations.
equal, you meant the thing that you wrote down with the 5 rules.
Yes.
Okay.
Yes, exactly. So, let this denote the category whose objects are category presentations and whose morphisms are equivalence classes of provably equal maps of category presentations. Now, we get an induced functor, and this becomes an equivalence. Okay?
You gotta put some restrictions on cat. You started off with sets of objects.
Yeah, I mean, yeah, you have to care about set theoretic difficulties,
Okay,
but I'm
don't.
sweeping it under the rug.
Oh,
Okay.
Well, anyway, if you're going to put the thing on a computer, you're probably going to take
Want
things that are
finite.
countable so you can put them as finite
Yeah.
expressions.
Yeah, put your favorite set theoretic restrictions here.
Can you just, I don't want to talk about set theory either, but it's definitely not a one-to-one function. The induced functor, it's not one-to-one, it's
One-to-one.
there are many presentations for every category.
Right.
Yeah, but he's saying he's saying he looked at equivalence classes of equivalent presentations.
The morphisms have been quotiented. So all of those presentations you can give will be equivalent.
Okay.
Any other questions?
And of course, as you mentioned computability, you obviously can't be sure to solve the word problem and show that two things are equal.
Yeah.
So this is
Very
obviously
different.
only, in principle, there is one, whether or
Yes.
not you can find it.
Yes, exactly.
Of course, cat is a two categories. What happened to that?
Yeah, that's another very good question. I can say more about that maybe a little bit later. There's a lot of different things we can consider here. I'm doing the most naive
Getting
kind
into
of
two-dimensional presentation.
Yeah.
This gets really complicated.
Exactly. But no, you're right onto a deep point that I will not talk about right now. Okay, so more examples. So what I showed you before was actually came from a category presentation, right? So the sorts are just employees and departments, the function symbols are these 3 function symbols and these 2 equations. And what I showed you was actually the semantics of this. It was a category presented by this. So the semantics has these morphisms and more.
Don't they use like the language of graphs and so on for this?
Yeah, I mean,
For this
people,
business?
yeah,
Well,
you could say that too.
like with many edges.
Yeah. I'm coming from using the language of like algebraic theories.
Well, sorts and function symbols form the graph, so
Yeah.
it was just a free category on that graph they formed.
So now, how do we define profunctor presentations? So first, let's give the following construction. If I have a profunctor from C to D, let P tilde denote the following category. So now we're in category theory land. There's no presentations, okay? So P is a profunctor. I'm going to define a category P tilde. Its objects are going to be the objects of C and the objects of D. And now I have to give you the Hom sets. So if I have X and Y and they both live in C, then all the morphisms are just going to be the morphisms in C. If they're both in D, it's just going to be the morphisms in D. And then I'm going to add these, the set from X to Y, where X is in C, Y is in D. I have a set, and I'm going to think of every element in that set as a morphism from X to Y. And then there's going to be none going backwards.
I see, and the point is you only have a C and D, so I don't have to worry about composing 2 B's, because once I get into D, I can't go down to anything other than composing with things that take me from B to D.
Exactly.
Is that P, X, Y, is it actually just the Cartesian product in some sense? Or no?
Well, P is a functor from C op times D to set. So if I have X and a Y and C and D, then this is just a set.
But I mean, you have X, a member of C, and Y, a member of D.
Yeah.
So for any X in C and Y in D, you can form the pair, or no?
Sure. In the category C op times D, that's an object.
Okay, I'll ask later.
Okay. So I've given you the Hom sets, and then composition of morphisms is defined using the functoriality of P. I call P tilde the collage of P, and this is a category. And you can think of it as a bridge from C to D going in one direction. Okay? So I have this collage of P, and there's a functor from P to 2. And 2 is a category with 2 objects and 1 non-identity morphism, 0 to 1. This functor sends C to 0, all of D to 1, and all of the morphisms acting as this bridge get sent to the morphism from 0 to 1. Okay? And in fact, we have these pullbacks, okay, in categories. These are strict pullbacks. So whenever I have a collage, C includes into it, D includes into it. Simple enough. So this construction defines a functor from the category of profunctors to categories over 2. Okay? And this functor is an equivalence. Every such...
You didn't talk about morphisms.
I didn't. I'm going to sweep that under the rug also, but it's in... When I have a fixed domain, profunctors from C to D, then it's just natural transformations.
Yeah, dinaturality doesn't come in there?
No, if I fix the domain and target, no. But here, yeah, if I have just floating like that, I have to have functors from C to D. But I'm not going to talk about that right now. So the point here is that I'm going to use collages to present profunctors. Okay? Because profunctors you can think of as certain kinds of categories. And I already told you what category presentations are. All right, so given category signatures sigma and sigma prime, and uncurried, so I'm going to use this terminology curried and uncurried, okay? So an uncurried profunctor signature, pi, consists of a set of function symbols that we're going to call the profunctor function symbols. And their source has to be in sigma, and the target has to be in sigma prime. So you imagine these are function symbols that are crossing that bridge. Now we define an associated category signature here to have the sorts of sigma and sigma prime and the function symbols of all of them. So imagine this is C, D, and then the function symbols crossing. Okay? Now a path in this category presentation, category signature, sorry, is a cross path if C is in sigma and D is in sigma prime. So there are other paths, right? We had all the paths in sigma, all the paths in sigma prime, and now we have these cross paths. And an uncurried profunctor equation is an equation between cross paths. Okay? Now, that was for signatures. Let's talk about the presentations. If I have two category presentations, C and D, a CD uncurried profunctor presentation consists of a pair, P sigma and PE, where P sigma is an uncurried profunctor signature from C sigma to D sigma, and PE is a set of uncurried profunctor equations. So remember, these are equations between cross paths. So here's an example. Say I have a category presentation here with two sorts and one function symbol, and I have this example we used before, then a profunctor function symbol E from managers to employees and D from department prime to department. And then I add a new equation here. Okay? So this is what a profunctor presentation looks like, an uncurried profunctor presentation. Okay. So if I have an uncurried profunctor presentation from C to D, we define the associated category presentation in kind of the obvious way. So the signature of this category presentation is just going to be the signature of the profunctor signature, and the equations are going to be all the equations of C, P, and D. And we say P is equal to Q if there are equations in PE. And we define this, a prox symbol, to be the restriction of the whole category just to the cross paths. So now I'm going to focus on quotienting but only by cross paths. Okay? Now a morphism of uncurried profunctor presentations is a function from the profunctor function symbols to cross paths. And such that this map, that the obvious induced map on the associated category presentations is a map of category presentation. And I'm going to let this denote the category of CD uncurried profunctor presentations. Any questions? All right, so we can define the semantics of this in kind of the same way as we were doing before, and we get a functor from uncurried profunctor presentations to the category of profunctors from the semantics of C to the semantics of D. Now, suppose that C and D are finite category presentations. So these are the ones we actually want to think about. So far we haven't put any restrictions on these presentations, but in real life we need to think about finite presentations, right? So when I say a finite category presentation, I mean there's finitely many sorts, finitely many function symbols, and finitely many equations. I say a profunctor from the semantics of C and D, so this is an arbitrary profunctor, is finitely uncurried presentable if there exists a finite uncurried profunctor presentation, which just means there's finitely many profunctor symbols and equations. I should have written equations also. Such that when I take the semantics of P, it's isomorphic to the profunctor we started with. Okay? So I'm looking now at a subclass of all profunctors. So this is the first theorem of the paper. The class of finitely uncurried presentable profunctors is not closed under composition. Okay? So here's the proof. It's basically just a counterexample. Okay? So C, D, and E are category presentations. C has one sort, no function symbols. D has one sort and one function symbol, a loop. E has one sort and no function symbols.
Could you just draw the diagram just on the black?
Don't worry, I have it on the next slide.
All right.
I'll just skip to the point.
Sorry, it just helps me see.
Yeah.
Thank you.
Category presentation C, D, and E. One sort, no function symbols. One sort, one function symbol. One sort, no function symbols. No equations. UnCurried profunctor presentation here with one function symbol and one function symbol here. Okay?
And what happens when I compose the P with the F? I guess it just stays as P is composed with F.
Yeah,
What do you
there's no
mean by that?
equations in the profunctor presentation.
That's right.
Okay,
That's
just
right.
want to be sure about that.
Exactly. Yeah.
All right.
Okay. So I have two profunctor presentations here, and then I take their semantics.
Yeah.
So that's P and Q here, and then I compose them. Now I gave the composition in terms of a coend, but you can kind of imagine just freely gluing them together. Okay, because there's no equations here, so that's what it'll actually be.
So there's all paths in that diagram.
All the paths in this diagram.
Including infinite of that, that's
Exactly.
the problem.
Exactly.
Sure.
Yeah.
So the set, so this right here is an actual profunctor, P composed with Q, right? And so the set here from C to E is a set of all paths. Well, there's infinitely many paths. I go P, and then however many times I want around F, and then Q. So this is an infinite set, right? Now, suppose R is an uncurried profunctor presentation from C to E, such that it has the semantics of this composition. Then R has to have infinitely many profunctor function symbols. Since there are no function symbols in C or E, there's no other way to get the function symbols. Therefore, this is not finitely uncurried presentable. Now, P and Q are obviously finite uncurried profunctor presentations. They only have one symbol each. But when I compose them, I got something that's not finitely uncurried presentable.
Right, the problem is once you integrate that D out in your coend, an infinite number of arrows showed up.
Exactly.
You gave a finite presentation of the infinite numbers.
So this is bad. This is a major defect of uncurried profunctor presentations. If I want to throw this into my computer and make some computations, I'm going to run into a big problem. So what do? Well, we try and come up with another notion of presentation where this defect doesn't exist. So that's what I'm going to do now. Okay? So the first thing I'm going to do, and the difference between the uncurried and the curried ones comes from how you think about profunctors. So in the uncurried one, you've kind of thought of it as from C-op times D to set. Now this other one that I'm going to introduce, you think of it as C-op to D sets. And I'll say a little bit more about that in a second. Okay? All right, so first let's define instance presentations. So for me, I don't like saying co-presheaf. So if I have a category C, an instance on C is just a co-presheaf, a functor from C to set, okay? But also notice that an instance is the same thing as a profunctor from I to C, from 1 to C, where 1 is the terminal category. So there's a category with one object and no non-identity morphisms, right? Now why is this an instance? Well, 1-op times C is isomorphic to C. So that's a functor from C to set. So let 1 denote the category presentation with one sort and no function symbols or equations. That obviously presents the terminal category. Given a category presentation C, an instance presentation on C is a 1C uncurried profunctor presentation. Okay? In other words, I set the category of C instances to be the uncurried profunctor presentations. So if I is an instance presentation on a category presentation C, we call the cross paths the generators of I. So this is how you can draw and how you can visualize the example we had before. You imagine that we have this new sort here, and all the arrows out of it are going to be generators. So before we had Alice, Bob, and Charlie, and we had computer science and math. And then the equations are going to tell you how to fill in the rest of the data. Okay? So Alice, her manager was herself. So that's an equation. Then I have dot, dot, dot here with all the other equations you need to fill in to actually get the data instance we had before. So this is an instance presentation. Okay, so now I'm going to give the definition of a curried profunctor presentation. So this is a profunctor presentation that's different. That's going to solve the problem we had with the other kind. Okay? So given category presentations C and D, a curried profunctor presentation, P from C to D, consists of an assignment of a D instance presentation to every sort of C. So this is what I was saying before. A profunctor from C to D is the same thing as a functor from C op to D sets. Okay? So to every C, I'm giving a D instance presentation. And for every function symbol in C, I want a morphism of instance presentations. Now the morphisms are already defined because they were examples of uncurried profunctor presentations. Okay? So that means to every function symbol I have a morphism of instance presentations going the opposite way. And I want one more thing, that if I have an equation of paths in C, I want to be able to prove that the resulting morphisms are equal. So I'm thinking this is a presentation of a profunctor like this, and that should be a COP. That all right with everybody? All right, so maybe I won't go through this in too much detail, but basically on this page, I'm giving the description of how to compose two curried profunctor presentations. Okay? So you think that P is a collection of instances on D, and Q is a collection of instances on E. Right? So now I want a collection of instances on E for every C. And I'm going to denote it using that symbol up there. Okay? So I want the generators of this instance to consist of pairs of generators, P from P of C and Q from Q of D. Whenever I have P going from C to D. So you imagine, like, if you just took the collages, you would just take the arrows and put them next to each other whenever they compose. Okay? And I'm going to write the new generator like that, with the tensor symbol. And that you can think of as going from C to E, because it's a generator of the instance P times Q on C. Now we extend this formal operator as follows. If I have a path in E, so on the right-hand side, then I set P times Q dot H, I just pop the H out. So now this is a path in the composite. If G is a path in D, then when I plug it in on the right side of P here, I want to slide the G over, but hit it with Q, because Q acts on paths. Okay? And then, so that's how I get the generators and how I get terms. Now I want to describe the set of equations. And it's very simple. It's just take all the equations on the left-hand side for every generator, and take all the equations on the right-hand side for every generator. And this gives me the generators in the equations. And then if I have a function symbol in C, then when I have an F here and I have a generator P times Q, I just hit it on the left-hand side to P. And then P is going to be something like F, F prime dot P dot G, and then you swap over the G there. And then the F would come out here. Is that all right?
Can you pass a curried profunctor presentation to an uncurried
Yes, you can.
profunctor presentation?
Yes, but you're getting ahead of me.
So I'm just saying, you should be able to put them on the same footing and compare them.
Exactly, exactly. So that's where we're going. That's where we're going. Any other questions? No. Okay.
Yeah, let me ask one question. I think you clarified this already. So you're saying the generators in this presentation are pairs of generators that line up on the dot?
Yes.
There's no intermediate morphism allowed?
Exactly. Yeah, and what's taking care of that intermediate thing is the action by Q. So if I have something on the right like that, it like slides through it. Okay, so the next theorem, if I have two curried profunctor presentations P and Q, there's an isomorphism here. So if I take the semantics, and you do it in the way that you would think, and I compose them, this is an isomorphism of profunctors, of actual profunctors. Okay. Furthermore, if P and Q are finite curried profunctor presentations, then clearly this is also finite curried, because everything there was based on finite information in the previous slide. So that leads to the following corollary. The class of finitely curried presentable profunctors is closed under composition. That's kind of a weird thing, right? I mean,
Could you go to a little example with the little tadpole loop?
the little tadpole loop.
That you had the, the PQ. What would this do instead? What would be the finite thing here?
Right.
So why you don't get in trouble?
Yeah. So the point is, I guess I can write here, or actually it would be better over here.
Oh, sorry.
So before we had, you all see that? Right? So this defined two uncurried profunctor presentations. Now there's a problem here if we want to define curried. Okay? Now this is perfect. This one's perfectly fine for curried. I just define the instance on D with one generator, P. But here, I want to define an instance on E, but I also have to define a morphism, because there's a function symbol here. So if I wanted to define Q of D as a curried, so I want to define a curried profunctor presentation from D to E, I would also not only just have to assign an instance presentation on E, I would also have to define a morphism. And what that would look like, semantically, is adding an equation like this. And basically what you would end up with in the semantic level is an extra equation, and this would be finite. Okay?
Right, so you still have the F around, so you can write F to the end rather than having to put it in a black box like you did before.
Exactly. Exactly. So there's this weird thing where if you have these left-hand paths, and you kind of like, they get stuck in the uncurried one. But for the curried ones, you have this extra morphism that's kind of getting rid of them, or passing them through in a way. All right, so we fixed our problem in some sense, right? We know that curried profunctor presentations compose. However, they're kind of annoying to work with if you work with them for a little while. They're more annoying than the uncurried profunctor presentations. And it would be convenient to know what class of uncurried profunctor presentations can be turned into curried ones, so what you were kind of thinking about before. Okay, so if I have a curried profunctor presentation, oh, and I should say what I mean when I say curried. So currying is just the process of going from like that. I say this is currying.
Yeah, the exponential adjunction.
Yeah.
The
Figured I should
computer
probably
scientist
say
term for
that out loud.
exponential adjunction.
All right, so if I have a curried profunctor presentation, then let P bar denote the uncurried profunctor presentation with function symbols for every generator. So it's kind of the obvious way of doing it. And the equations are defined similarly. And we obtain a functor from the curried presentations to the uncurried ones. Now that functor, this functor is non-equivalent in general. Okay. So we want to find some subcategory such that it becomes an equivalence. All right. So now suppose I have an uncurried profunctor presentation. By a short left path, we mean a path in P of the form f dot P, where f is a C function symbol and P is a profunctor function symbol. Okay? So on the left, you could have a whole path, but when I say a short left path, I mean just a function symbol. So you imagine just going one in C and then crossing the bridge, and that's it. That's a short left path. By a right path, I mean one of the form P dot G, where G is a path in D. So I cross the bridge, and then I'm allowed to go wherever I want in D. Okay, so that's a right path. So P is non-generative if for every short left path, L in P, there exists a right path that's provably equal to it. Okay?
I see, so it sort of means, okay, if I have something in front of the P, I can move it through and
Exactly.
get stuff on the other side.
Exactly.
I can move it across the bridge, so to speak.
So you can see how that kind of plays with the previous example. Because f dot q is a short left path. And since in the uncurried one, there's no right path that it's equivalent to. Okay?
Let me just ask a technical question. Did you mention earlier the square root of 2?
No, that's not a part of it.
Please forgive me for bragging, but at dinner I will explain the connection.
Excellent. Can't wait. Okay. Anyway, so if I have an uncurried profunctor presentation P, let P and C is a sort in big C, then let P upper C denote the D instance with generators P for every profunctor function symbol. So basically, what I'm going to do here is I'm going to take a whole uncurried profunctor presentation and only look at the things coming out from one sort. Okay? And that's going to give me a new uncurried profunctor presentation, and I want to consider only the equations where the left-hand side is coming from C. So I'm allowed to prove things on the right, but not on the left, if that makes sense. Now we say P is conservative if for every pair of right cross paths in P, if I can prove they're equal in P, then I can prove they're equal only by using things on the right. Yeah, so that's what I just said. So we have two conditions on an uncurried profunctor presentation: non-generativity and conservativity. Now, for every sort there's an inclusion functor from the semantics of PC to the semantics of P. And now we have a proposition that P is conservative, that condition I gave before, if and only if that functor is faithful for every C. And it's non-generative if and only if this function is surjective for every D. You want to be able to say it's full, but you run into the problem of if you do C to C, then it might not be surjective. But it's surjective away from just that one counterexample. So full and faithful, basically. Right. So call an uncurried profunctor presentation P curryable if it is conservative and non-generative. Let this denote the subcategory of uncurried presentation on the curryable profunctor presentations with what I call rightward morphisms. So these are morphisms here of uncurried profunctor presentations that send cross paths to right paths. So there's constantly this problem of having to, you always want to be able to move to the right. Okay, so, but this is kind of technical. But this is what you need in order to get this following theorem that says this functor lands in this subcategory. And if we restrict the codomain to this subcategory, then this functor becomes an equivalence. So the uncurried profunctor presentations that are equivalent to the curried ones, we call curryable, and they are precisely characterized by these two properties. And then you have to be a little careful with the morphisms. Okay. And yeah, so that's what we did. We characterized precisely the uncurried profunctor presentations that are equivalent to the curried ones. And I think this is a great starting point for investigating more deeply presentations of categorical structures. You know, this theory has a long history of, you know, giving presentations and whatnot, but yeah, I was surprised to see that this kind of simple idea I couldn't find anywhere in the literature. But yeah, so that's it. Thank you so much for your patience and attention. Oh, and I have a bonus slide. I have a bonus slide for people who like this kind of stuff. The category presentations, maps of category presentations, and curried profunctor presentations form a double category. Okay, so if you like double categories, here's an example of one. And then if you quotient it in an appropriate way, you get another double category, and that's equivalent to prof. So, yeah, fun bonus slide. That's it. Thank you, guys.
Any questions? Very clear.
I've got too many, so I won't bring up any of them.
Yeah,
Well,
sure.
yeah, maybe I've squared of two questions.
Yeah.
Sure. I'll start off by asking a literature question, which I don't know the answer to. Where can I read a beginner's presentation of, and we once discussed this last year or two, whatever it was. There are, pre-sheaves are not the same as sheaves.
Right.
There is the wonderful square root of the thing that takes a pre-sheaf to
You mean the
a
plus
sheaf.
construction?
The what?
You mean the plus construction? They
The
have
plus
to do twice
construction,
to
right.
get a-
But what I'm interested in is something even more naive and elementary. It is implicit in every textbook and article on modern algebraic topology since Poincaré. Where can I read a beginner's presentation of all the obstructions? You know, a pre-sheaf isn't, some pre-sheaves are not sheaves.
Right.
So one could classify in the usual way that we now know for the order of 100 years. We can classify as a first cut all the obstructions. Where can I read about this?
I mean, there is no obstruction because you have sheafification, right? I mean,
Oh, okay, we ran into this on 30. No, I'm saying something that's not false in that way.
All right.
It's false doubtless in another way, but not that particular. Thanks.
yeah.
End of race.
So as you said, you've got more data that you're carrying around when you've got your curried gadget.
Yes.
UnCurried gadget.
Yeah.
And the data is because we're really looking at maps between instances,
Yeah.
not maps between schemas.